Here we have our last section that we're going to cover in Survey of Calculus. At least right now. We may add more in future classes. So maybe if you're taking this class sometime after summer of 26, maybe we have more. But initially, this is where we're ending. So Fundamental Theorem of Calculus, which is kind of interesting that we get to this at the very end, the Fundamental Theorem, and it's the last thing we cover. It seemed like it'd be earlier, but it is so named, and it does happen to be the last thing that we're getting to. So let's talk about it. So we have f is some continuous function on some interval a to b, and we're going to let the capital F be the antiderivative of f, be any. So again, because when you take the antiderivative, you always have the plus c. So even in this case, the plus c doesn't really matter what we're doing. So it could be any antiderivative. Then the integral from a to b of lowercase f of x dx is just going to be the antiderivative evaluated at b minus the antiderivative evaluated at a. So to evaluate this expression here, we find the antiderivative, and then we plug in the upper limit b, and then we plug in the lower limit a, and then we subtract f of b minus f of a, capital F of b, capital F of a. So let's see how this works. If you're good at antiderivatives, then this is a fairly easy process. So we have 3x squared. We need to find the antiderivative. That's just going to be x cubed. Now, typically, after we find the antiderivative, we use this long vertical line and we put our limits. So now we found the antiderivative, and now we're going to plug in these limits. So we plug in 3 for x, so we have 3 cubed minus 1 cubed, and of course that's going to be 27 minus 1, which is 26. So no big deal. Usually the integrating or the finding of the antiderivative is the trickier part on these problems. So let's look at some properties of definite integrals. And I think we saw a couple of these with just the general antiderivatives. Same thing applies. So we have some constant k times a function. We can pull the k out in front of the integral and just have k times the integral of f of x from a to b. If we have the sum or difference, we can separate the integrals. So we can write this as the integral of f of x plus or minus the integral of g of x. So I don't think those are new. We've seen those before, and they make a lot of sense. Now this next one, let's talk about this one. So we have the integral from a to a. Now, if we evaluate this would, so let's say capital F is the antiderivative, then we'd evaluate this at a, and then we'd have capital F of a minus capital F of a, which is, of course, 0. So if the limits of integration are the same, it doesn't really matter what the antiderivative is, the evaluation of this expression is going to be 0. Then let's evaluate this. So if we evaluate this using the fundamental theorem, we'd write this as f of b, capital F of b minus capital F of a. And what we can do is we can reverse these, or let's factor out a negative. So we could write this as negative capital F of a minus capital F of b. So all we're doing, basically reversing the order and then pulling out the negative. And now what is this? This is going to be, so let's have a negative here for that negative. And then if we take this in the reverse order through the fundamental theorem, now the upper limit is a and the lower limit is b, and we can integrate f of x. So the integral of from a to b of f of x is equal to the negative integral from b to a. So if you switch the limits of integration, you can pull out a negative, and you have the opposite effect on your answer. Now this one here, we're going to look at what happens if we split this up. So if we have the integral from a to b, we can write this as the integral from a to c of f of x dx. plus the integral from c to b f of x dx. And how does this work? Well, and maybe we could have written this as intermediate step, but we'll say for some c in this interval between a and b. And I guess if c is equal to a or equal to b, then it doesn't matter, because if it's equal to a, then this one is just 0, and we just have the same thing. So it's not even really worth mentioning. But we could keep this as a closed interval, but more useful when c is not a or. Now, if we evaluate these, we get so evaluate this one, and I guess we'll do this underneath. This would be capital F of C minus capital F of A. And then this one would be capital F of B minus capital F of C. Now, if we're adding these two, and of course the F of C's will cancel, and then this is just capital F of B minus capital F of A. So still works out. So basically, you can divide this interval up however you want. So if you were integrating from 0 to 1, you could divide it up as 0 to 1/2, and then 1/2 to 1, or 0 to 1/3, 1/3 to 1. Like, it doesn't matter. And so you can divide it up, and you can divide it up as many times as you want. So it could be more, could be 2 times, or it could be, you could say A to C, C to D, D to B, or however many times you want to do it. But that can sometimes be helpful to do that. All right, so let's look at this one. Just again, a standard antiderivative, no big deal here. So just use the power rule term by term. And so integrate 2x to the third, we get 1/2 x to the fourth, minus integrate negative 3x, we get minus 3/2 x squared, and then integrate 4, and we get 4x. And then we evaluate that from 3 to 5. So plug 5 in, we get 1/2 times 5 to the fourth minus 3/2 times 5 squared plus 4 times 5, and then minus, now let's put parentheses, we're going to subtract all of these evaluated at 3. So we have 1/2 times 3 to the fourth minus 3/2 times 3 squared plus 4 times 3. All right, so we get 5 to the fourth, I think is 625 halves. 5 squared would be 25, so that'd be minus 75 halves, plus 20, minus 3 to the fourth is 81 halves. This would be 27 halves, and then plus 12. All right, so a bunch of fractions here. Let's just get out the calculator. So I guess it's 496 over 2, which is 248 plus 20 minus 12. And so we should get 256. All right, so again, usually the tricky part is the integrating. This one's not too tricky if you've been practicing your integration since we started chapter 7. But probably where most people will make a mistake, and maybe I did, I don't know, I don't think I did, but evaluating these and doing this arithmetic is probably where people are more likely to make mistakes. So try to be careful when you're doing that. All right, so let's look at the next one. If this will scroll down, there we go. So evaluate the definite integral, e to the 2u plus 1 over u plus 4 squared. So maybe we need to do a substitution on this one. So normally we do a u substitution, but we already have u in here. So let's let w equal u plus 4, and then dw will equal du. And so let's split this one up. Integral from 1 to 2 of e to the 2u du minus the integral from 1 to 2, 1 over u plus 4 squared du. So we can do this one. If you need substitution, maybe you could use it, but we're just going to divide by the derivative of this. So 1/2 e to the 2u. And you can check that if you need to. Evaluated from 1 to 2. Now, let's look at our substitution. Now, what you can do with this, and a lot of times, most textbooks actually do substitution after this section, but we hadn't gotten to definite integrals when we did substitution, so we'll learn this now. When you do a substitution on a definite integral, you can actually plug these limits in for u and see what the corresponding w is. So when u is 1, plug in 1, and w is 5. When u is 2, plug in 2, we get 2 plus 4, so w would be 6. So now we're changing the limits of integration, so now when we evaluate the integral, we don't have to substitute back. So we're going to do the integral. For now, instead of from 1 to 2, it's from 5 to 6. And this will be 1 over w squared dw. So very simple substitution, but it's pretty important to learn this trick of changing the limits. If you take the Calculus 2 course, you'll probably be doing this at some point. All right, so let's evaluate this. So we have 1/2 e to the 4th minus 1/2 e squared. Now we didn't change this variable, so we don't need to change these limits. So we're keeping since we kept the u in here, we keep the 2 and the 1. Now, this would be, so let's just rewrite this real quick, is w to the negative 2. So we're just going to rewrite that. So we add 1 to the exponent, divide. We already have the negative here, so this would be a plus 1 over w. And this is evaluated from 5 to 6. So we have 1/2 e to the 4th minus 1/2 e squared plus evaluate at 6, so 1/6 minus evaluate at 5, 1/5. And if we want to combine those, we get probably 1 over 30, negative 1 over 30. So 1/2 e to the 4th minus 1/2 e squared minus 1/30. Okay. So a little substitution trick here. If you're not comfortable with this yet, then when you get to here, you can just plug u plus 4 in again. 1 over u plus 4. Keep the 1 and the 2, the original limits. Don't change the limits. So that's kind of optional. In this case, it doesn't really matter which way you do it. Other times, it's easier to not substitute back. So it just kind of depends on the problem. The more complicated the problem is, the more likely it is that you probably want to change your limits like this. All right, so let's look at another one. Here we have integral from 1 to 3, 18 times ln x to the 5th over x. So this one is going to be another substitution. So now before I tell you, maybe think about what the substitution might be. Typically, if you have an ln of x, that's going to be what you're substituting. So let's do that one. So u is ln of x, du is dx over x, or 1 over x times dx. And then let's change these. So if u is, actually we'll do the top, we'll keep it in order here. So if u is 3, or actually x is 3. If x is 3, because that's what we started with. If x is 3, u is ln of 3. Now don't evaluate that, just leave it ln 3. If x is 1, u is ln of 1, which is 0. So this changes our integral from 0 to ln of 3. Now, this may look a little bit weird because we're used to seeing just regular numbers, but ln of 3 is just a number, so it's fine. Let's do our substitution. So we can actually pull this 18 out. So you can pull the constant out. And then this will just become u to the 5th And then we have dx over x, so that is our du. And then we can integrate that. The new exponent will be 6. 18 over 6 will be 3. So that's 3 u to the 6th. Don't need the c. I guess I didn't mention that as we were starting to work these. But when you do a definite integral, you don't need to put the c. And I can show you why. It actually doesn't matter if you do it, but you don't need to because it doesn't change anything. So now we plug in 0. This will obviously be 0, so we don't even need to worry about that. Let's just put ln, or 3, ln of 3 to the 6th. Okay. All right. So going back to the constant thing, if we did put a plus c in here, so we integrate 18 ln 3 0 u to the 5th du, and let's say we put the c in 3 u to the 6th plus c. Evaluated from 0 to ln of 3. So plug in the ln 3. Now, c is not affected by either of these because c is just a constant, so plus c. And then minus, now plug in 0, so we get 3 times 0 to the 6th plus c again, because c, 0, there's nothing to plug in, it's just a constant. So now we have 3 ln 3 to the 6th plus c minus 0 minus c, and these cancel out. And that's the way it'll always be, because you always have one c here for the upper limit, and then you'll have another c here for the lower limit, and you're subtracting, so they always cancel out. So you end up with the same thing.